So hello everyone and welcome to NEETOPEDIA, that is NEET ka encyclopedia, and today we are finally going to kick off our P block elements by finishing off with group 18 elements. Please note that group 13 to 17 of the P block elements has been already uploaded on our channel. Kindly check out the chemistry audiobook playlist for that. Also, do not forget to like, share and subscribe to the channel. So without wasting our time, let's get started. 7.23 Group 18 Elements. Group 18 consists of elements like helium, neon, argon, krypton, xenon, radon and oganesson. All these gases are chemically unreactive. They form very few compounds. Because of this, they are termed as noble gases. 7.23.1 Occurrence. All these gases except radon and oganesson occur in the atmosphere. The atmospheric abundance in air is 1% by volume, of which argon is the major constituent. Helium and sometimes neon are found in minerals of radioactive origin like pitchblende, monazite, cleverite. The main commercial use of helium is a natural gas. Xenon and radon are best elements of the group. Radon is obtained as a decay product of radium-226. Oganesson has been synthetically produced by collision of Cf249 atoms and calcium ions. Example 7.20. Why are elements of group 18 known as noble gases? Solution. The elements present in group 18 have their valence shell orbitals completely filled, and therefore they react with very few elements only under certain conditions. Therefore, they are known as noble gases. Oganesson has its symbol Og, atomic number 118, atomic mass 294 and electronic configuration as radon 5f14 6010 7s2 7p6. Only very small amount of Og has been produced. Its half-life is 0.7 milliseconds. Therefore, mainly predictions about its chemistry have been made. Here, except for oganesson, important atomic and physical properties of other elements of group 18 along with their electronic configurations are given in table 7.12. The trends in some of the atomic, physical and chemical properties of the group are discussed here. 7.23.2 Electronic configuration. All noble gases have general electronic configuration as ns2np6 except helium, which has 1s2. Many of the properties of noble gases, including their inactive nature, are ascribed to the closed shell structures. 7.23.3 Ionization enthalpy. Due to stable electronic configuration, these gases exhibit very high ionization enthalpy. However, it decreases down the group with increase in atomic size. 7.23.4 Atomic radii. Atomic radii increases down the group with increase in atomic number. 7.23.5 Electron gain enthalpy. Since noble gases have stable electronic configurations, they have no tendency to accept the electron and therefore have large positive values of electron gain enthalpy. Physical properties. All the noble gases are monoatomic. They are colorless, odorless and tasteless. They are sparingly soluble in water. They have very low melting and boiling point because the only type of interatomic interaction in these elements is weak dispersion forces. Helium has the lowest boiling point of 4.2 Kelvin of any known substance. It has an unusual property of diffusing through most commonly used as laboratory materials such as rubber, glass or plastics. Example 7.21. Noble gases have very low boiling points. Why? Solution. Noble gases being monoatomic have no interatomic forces except weak dispersion forces, and therefore they are liquefied at a very low temperature. Hence, they have low boiling point. Chemical properties. In general, noble gases are least reactive. Their inertness to chemical reactivity is attributed to the following reasons. Number 1. Noble gases except helium have completely filled ns2np6 electronic configuration in their valence shell. Number 2. They have high ionization enthalpy and more positive electron gain enthalpy. The reactivity of noble gases can be investigated occasionally ever since their discovery, but all attempts to force them to react to form compounds were unsuccessful to a quite few years. In March 1962, Neil Bartlett, then at University of British Columbia, observed the reaction of a noble gas. First, he prepared a red compound which is formulated as O2 plus PtF6-. Then he realized that the first ionization enthalpy of the molecular oxygen was almost identical to that of xenon. He made efforts to prepare same type of compound with xenon, which was successful in preparing another red color compound, Xe plus PtF6- by mixing PtF6 and xenon. After this discovery, a number of xenon compounds, mainly with most electronegative elements like fluorine and oxygen, have been synthesized. The compounds of krypton are fewer. Only difluoride KrF2 has been studied in detail. Compounds of radon have not been isolated but only identified, example RnF2, by radio tracer technique. No true compounds of argon, neon or helium are yet known. Number A. Xenon fluoride compounds. Xenon forms three binary fluorides XeF2, XeF4 and XeF6 by direct reaction of elements under appropriate experimental conditions. XeF6 can also be prepared by interaction of XeF4 and O2F2 at 143 Kelvin. XeF2, XeF4 and XeF6 are colorless crystalline solids and sublime readily at 298 Kelvin. They are powerful fluorinating agents. They are readily hydrolyzed even by traces of water. For example, XeF2 is hydrolyzed to give XeHF and O2. The structures of the three xenon fluorides can be reduced from VSEPR, and these are shown in figure 7.9. XeF2 and XeF4 have linear and square planar structures respectively. XeF6 has 7 electron pairs, 6 bonding pairs and 1 lone pair, and would thus have a distorted octahedral structure as found experimentally in the gas phase. Xenon fluorides react with fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoroions. Number B. Xenon oxygen compounds. Hydrolysis of XeF4 and XeF6 with water gives XeO3. Partial hydrolysis of XeF6 gives oxyfluorides XeOF4 and XeO2F2. XeO3 is a colorless explosive solid and has a pyramidal molecular structure. XeOF4 is a colorless volatile liquid and has a square pyramidal molecular structure. Example 7.22. Does the hydrolysis of XeF6 lead to a redox reaction? Solution. No. The products of hydrolysis are XeOF4 and XeO2F2, with the oxidation states of all the elements remain the same as it was in the reacting state. Uses. Helium is a non-flammable gas and light gas. Hence, it is used in filling balloons for meteorological observations. It is also used in gas-cooled nuclear reactors. Liquid helium finds use as cryogenic agent for carrying out various experiments at low temperatures. It is used to produce and sustain powerful superconducting magnets, which forms an essential part of modern NMR spectrometers and magnetic resonance imaging (MRI) systems for clinical diagnosis. It is used as a diluent for oxygen in modern diving apparatus because of its very low solubility in blood. Neon is used in discharge tube and fluorescent bulbs for advertisement display purposes. Neon bulbs are used in botanical gardens and in greenhouses. Argon is used mainly to provide an inert atmosphere at a high temperature metallurgical processes and for filling electric bulbs. It is also used in laboratory for handling substances that are air sensitive. There is no significant use of xenon and krypton. They are used in light bulbs designed for special purposes. I'm skipping the in-text questions for you to solve it later, or you can pause the video and solve it right now. Summary. Group 13 to 18 of the periodic table consists of p block elements with their valence shell electronic configuration ns2 and p1 to 6. Group 13 and 14 were dealt in class 11th. In this unit, remaining groups of p block will be discussed. Group 15 consists of 5 elements, namely nitrogen, phosphorus, astatine, antimony and bismuth, which have general electronic configuration as ns2 and p3. Nitrogen differs from other elements of this group due to small size, formation of p pi multiple bonds with itself with highly electronegative atom like oxygen or carbon, and non-availability of d orbitals to expanded valence shell. Elements of group 15 show gradation in properties. They react with oxygen, hydrogen and halogens. They exhibit two important oxidation states, +3 and +5. But +3 oxidation state is favored by heavier elements due to inert pair effect. Dinitrogen can be prepared in laboratory as well as on industrial scale. It forms oxides in various oxidation states as N2O, NO, N2O3, NO2, N2O4, and N2O5. These oxides have resonating structures and have multiple bonds. Ammonia can be prepared on large scale by Haber's process. HNO3 is an important industrial chemical. It is a strong monobasic acid and powerful oxidizing agent. Metals and nonmetals react with HNO3 under different conditions to give NO or NO2. Phosphorus exists as P4 in elemental form. It exists in several allotrope forms. It forms hydride PH3, which is a highly poisonous gas. It forms two types of halide, PX3 and PX5. PCl3 is prepared by reaction of white phosphorus with dichlorine, while PCl5 is prepared by reaction of phosphorus with SO2Cl2. Phosphorus forms a number of oxoacids depending upon the number of POH groups. The basicity varies. The oxoacids which have pH bond are good reducing agent. The group 16 elements have general electronic configuration Ns2Np4. They show maximum oxidation state +6. Gradation in physical and chemical properties is observed in group 16 elements. In laboratory, dioxygen is prepared by heating KClO3 in presence of MnO2. It forms a number of oxides with metals. Allotropic form of oxygen is O3, which is highly oxidizing agent. Sulfur forms a number of allotropes of this. Beta and alpha forms of sulfur are most common. Sulfur combines with oxygen to give oxides such as SO2, SO3. SO2 is prepared by direct union of sulfur and oxygen. SO2 is used in manufacture of H2SO4. Sulfur forms a number of oxoacids. Amongst them, the most important one is H2SO4. It is prepared by contact process. It is a dihydrating and oxidizing agent. It is used in manufacture of several compounds. Group 17 of the periodic table consists of the following elements: fluorine, chlorine, bromine, iodine, and astatine. These elements are extremely reactive and as such are found in the oxidation state can be +7. They show regular gradation in physical and chemical properties. They form oxides, hydrogen halides, interhalogen compounds, and oxoacids. Chlorine is conveniently obtained by reaction of HCl with KMnO4. HCl is prepared by heating NaCl with concentrated H2SO4. Halogens combined with one another to form interhalogen compounds of type XX1, where X1 is lighter and X. A number of oxoacids of halogens are known. In the structures of these oxoacids, halogen is central atom which is bonded to each case with one OH bond as XOH. In some cases, X is equal to 0 bonds are also found. Group 18 of the periodic table consists of noble gases. They have Ns2Np6 valence shell electronic configuration except helium which has 1s2. All the gases except radon occur in nature. Radon is obtained by decay product of radium-226. Due to complete octet of the outermost shell, they have less tendency to form compounds. The best characterized compounds are those of xenon with fluorine and oxygen only under certain conditions. These gases have several uses. Argon is used to provide inert atmosphere. Helium is used in filling balloons for meteorological observations. Neon is used in discharge tube and fluorescent bulbs. Okay, so that's it for today. We are finally finishing the P block elements. See you soon in another video. Till then, subscribe to the channel and stay tuned. Thank you.